Good evening everyone. Today I will be presenting fundamentals of XAS and how to process the data in the software. So here it is the schematic view of how the measurement is done. So basically this is the synchrotron source, and from here by using monochromatic beam is generated by using many mirror and monochromator, and after that we utilized this monochromatic X-ray fall on the sample, and it is transmitted and to get transmitted data, and also from the fluorescence X-ray we can measure this fluorescence data. Okay, so outline of the presentation is first we will talk about the fundamental of XAS, then XAS data reduction or processing method, then modeling of XAS data, and Zen's interpretation. And the presentation is based on these 4 references. So X-rays are light, which consist an energy range from 500 electron volt to 500 kilo electron volt with a wavelength of 25 angstrom to 0.25 angstrom. And the interesting thing is, in this energy region, light is absorbed by all matter through photoelectric effect, and that is why we can utilize X-ray to study many property of our material. So what is this photoelectric effect? So when a X-ray falls on the sample, so if its binding energy is lower, or if the energy of X-ray is higher than the binding energy of the core level electron of the material, then this electron will absorb the X-ray, and basically this electron will absorb and emit it from the system. So these phenomena, like how much it is absorbed, and that is I0 is the initial intensity of the X-ray, and how much is the coming out, how much electron is coming out with how much energy, that is I. So from here I equal to I0 e to the power minus mu t, where I is intensity transmitted through the sample, and I0 is X-ray intensity incident on the sample, and mu is the probability of X-ray absorption, and T is sample thickness, and we all are familiar with this Lambert-Beer's law. And where mu depends on this rho, that is sample density, atomic number, atomic mass, and X-ray energy. So basically XAS is a measure of the intensity of this mu, that is probability of absorption coefficient, mu as a function of energy near and at energy just above the absorption edge. So that means what is this? Basically this absorption edge. Now when X-ray energy is equal to the binding energy of the core level electron, there is a sharp rise in absorption, and that rise is named as absorption edge, that we will see in the later spectrum. So now what can happen when this, in the photoelectric effect, when an electron goes out from this core level, then there is a hole. Now to stabilize the system, one electron from higher level can means two multiple phenomena can happen. So one electron from higher level can come to fill up this hole, and now when it come from higher to lower energy level, so it will emit radiation. It can, if it come from L cell, then it is named as K alpha, or if it come from M, then it is named as K beta. So and this is also named as X-ray fluorescence. And the another possibility is that when this electron is coming from higher level to lower energy level, the emitted energy it transferred to the nearby electron. Then the nearby electron go to the continuum by releasing energy. Go to the continuum by releasing energy, and this process is Auger effect. So both the process can undergo, and now it also, now which process will undergo, that depends on the energy of X-ray that we are using. It also depends on the atomic number of the material. So now X-ray XAS measurement is mostly done in 2 modes. One is transmission geometries and one is fluorescence geometries. What is this transmission? I have already shown you in the first slide that if intensity I0 is passing through the sample and after the absorption it is going out as I. Simply how this measurement of this is named as transmission, and fluorescence means when this process is going on and emitting X-ray. So these two are detected with different detector and we can collect the corresponding data. In case of transmission geometry, this mu E equal to log I0 by I. This mu E represents energy dependence of the absorption coefficient, and this is our point of interest in XAS, where IF is the intensity of the fluorescence line. So in case of fluorescence, this mu E is proportional to IF by I0. So you can see that they are differed by this log. And this mu E, that is energy dependence of the absorption coefficient, depends on two parts. One is the atomic part, that is we can say that the how much absorption is there or absorption coefficient by a single atom. And another part, this one is the scattering of the photoelectrons by the surrounding atom. So that means once the photoelectron goes out from the system, so it cannot completely go out from the molecule. So it can get scattered with the nearby electron. So that scattering effect is considered here. Now this is the typical spectrum. XAS spectrum looks like. So here it contains two parts. One is XANS and another is XAS. So this XANS means X-ray absorption near edge structure. Now near edge, why? Because we have already seen that there is a absorption edge. This hard rise is named as absorption edge. With typically within 30 electron volt, that portion is considered as XANS. And the rest of the portion, this oscillation, this one which comes because of the scattering of the photoelectrons by the surrounding atom, which results in XAS. And here you can see that this red colored line, this one is for basically if we do not consider this oscillation, so this one is mu 0 E, that is absorption coefficient by a single atom. Now I already told that XAS is oscillation well above the absorption edge, and it is possible to quantitatively interrupt this XAS part, but for XANS it is qualitative in nature. So this XAS is represented with this equation where chi E equal to mu E minus mu 0 E divided by delta mu 0 E, where chi E is extended fine structure function of XAS. This actually represents the XAS part, and mu is the measured absorption coefficient. Mu 0 is smooth background function or absorption by an isolated atom, and delta mu 0 is measured jump in the absorption mu E at the threshold energy U0. That is this jump, this sharp rise in absorption, this part. And now if we want to consider this XAS, then it is always better to understand XAS in terms of wave behavior. So that means we have to convert this X-ray energy in terms to wave number. So it is represented with k equal to root over of 2m e minus e0 divided by h cat square. So with the help of the software, we convert this XAS part that I have shown you in the graph in terms of k, that is wave number. And we always use this XAS with chi k, where this chi k is oscillation as a function of photoelectron wave number, and basically this chi k is simply referred to as XAS. So now to represent XAS data, so first one is, this is the isolated part, this chi k, and this one is also converted in the wave number x-axis. So there are multiple oscillations there. To enhance this oscillation frequency, so we usually we multiply this chi k with k2 or k3 to enhance the oscillation. So this is the multiplied with k2, and where the frequency or oscillation is high, there that part will be intensified. Now to visualize the XAS data or interpret this data, we convert this K-space data into R-space, that is Fourier transform. Fourier transform of this data results to this portion. So from here we can interpret easily that this usually at less than 2 angstrom metal oxide or metal sulfide, all these bonds comes, and within beyond 2 or between 2 to 3 angstrom this metal bond come. So from here we can interpret the presence or absence of any metal oxygen or metal bond within the system. Now so till now I already discussed that we get XAS data and how we separate out these ZENS and XAS. Now once you get the data, how you are going to process it in the software. So initially I already told that there are two modes. One is transmission and another is fluorescence. So you can collect data in both the method at a single time, and basically the data output from the both the modes ideally should be equal. So you can use any of the data, either transmission data or fluorescence data. And also one more thing, like whether your which data will be good, that depends on your sample, or sample is on the substrate or it is a powder sample. It depends also on the sample preparation or the nature of the sample. So so step by step I will cover this data processing. First, this is the collected data. We collect in terms of mu E, that is the absorption coefficient with respect to energy. So first you have to make a pre-edge line, that is subtract a smooth pre-edge line from this mu E to get rid of any instrumental background or absorption from other edges. So once this pre-edge line is removed, then you can perform the normalization, this one. So this panel shows the corresponding normalized data. Now once you normalize, then identify the threshold energy E0, typically as the energy of the maximum of the first derivative. So this is our main spectrum. We can convert it into the first derivative, that is d mu E by dE. So red color represents the first derivative spectra. So here the maxima of the first derivative peak actually represent this threshold energy E0. Now next you remove the smooth post-edge background function to approximate mu0 E. That is mu0 E is I told that the absorption by a single absorption coefficient of a single in atom. So you remove the postage. Once this postage background function is removed, one should be very careful that it should not be spined. The red color, the line should not match with this blue color oscillation. Then your output data will be wrong, or you can get some wrong interpretation of the data. So basically this red color line should only match at this higher energy region, but not at lower energy. So one should be very careful with this part while doing post-edge background subtraction. Now you have isolated this XAS data from this part. Till now normalization is done. So now if you isolate this XAS part, this one, so this one we represent in chi k versus k, that is in terms of wave number, then multiply with k2 to increase the oscillation part, which looks like this one. Then we are going to convert this part into R space or Fourier transform. Now when you convert, you can actually select a region from in this case they have selected a region from this 2 angstrom inverse to around 13 angstrom inverse. So usually mostly till 12 or 13 angstrom inverse, around this range is considered. And one also needs to be careful about this part, that there should not be too much noise. If the noise also contributes in the oscillation, then also the output of the data in the Fourier transform will be different. So once you convert your XAS data in the K space, then you can convert this K space data into Fourier transform. So this is the corresponding Fourier transform data of this XAS. So from here, this represents this iron oxygen bond, this one is iron iron bond. Now this here in this figure, this red one shows real part. Actually the whole equation of this R space equation consists real part and imaginary part. So here in the fig plot, this real part is shown with the red and the blue part is the total. So now by this time you get your both Zen's data and you separate out your XAS part, and XAS part you convert into K space to R space. Now from the converting data to R space, now if you want to get data in more quantitative manner, so that time you have to perform XAS modeling. So what is this? XAS modeling is done by following this equation. So here in this equation there are few unknown parameter and few known parameter. So first of all, this Fk, this one, and delta K, these two represents scattering properties of the atoms neighboring the excited atom. So these two part is very sensitive, that is scattering property is very sensitive with the nearby atom. So that's why XAS gives us information about the nature of the coordination cell or nature of the nearby atom. So and while fitting this, you can get the value of these two parameters Fk and delta K by theoretically modeling the standard available CIF file. You can use it by using this FEFF program. So once you get these two parameters, then you can start fitting your XAS. From there one can get this n, that is number of neighboring atoms, r is the distance of the neighboring atom, sigma square is the neighboring distance. Now while you are fitting, one can think that from which data one should fit, because for XAS we have two kind of data. One is K2 weighted data, that is in K space, and another is Fourier transform R space. So it is always recommended to start fitting with this R space, because in this case we can select a particular range, like first means basically we can perform fitting in much more simple form. So in this case, if we start fitting with this Fourier transform data, we can first select a region from 0 to 2 angstrom. So that means we will consider only iron oxygen bond and perform the fitting. Then once fitting is done, then we can select the next region till 3 angstrom and perform the fitting to get iron for the iron bond. Now if our point of interest is only these two, then we can finish stop with this fitting. Now while you fit, you should be careful that the goodness of fit should be close to 1, and other parameters should also match. This here in this case, this red one represent fitted data and blue is the raw data. Now once your fitting is done, you get the corresponding R, N and sigma square, then you put this value to fit this K space data, because now you already know all the value in the equation. So then you can fit and recheck whether your fitting is good in the K space also or not. Now this one I already told about XAS part. Now from the Zen's part, we can qualitatively interpret data. Since Zen's is a much larger signal than XAS, so Zen's can be done at lower concentration and at less than perfect sample condition. And interpretation of Zen's data is qualitative in nature. And one more thing is, like, we can measure these XAPs with amorphous sample also. It is not always needed that the sample should be highly crystalline, because we are looking local property of the atom. Because when a photoelectron goes out, then it is the corresponding scattering is going on locally with the nearby atom. And here these genes, the age, position and shape is sensitive to formal valence state, ligand type and coordination environment. And an important and common application is to use the shift of the age position to determine the valence state. So here in this figure you can see the corresponding XAPS data for iron oxide and metallic iron with iron in multiple oxidation state. You can see that there is a clear change in the nature of the peak, as also their corresponding age energy is shifted according to their this formal valence state or ligand type or coordination environment. Apart from this, one can interpret the corresponding geometry, that is, it is a regular or distorted octahedral or tetrahedral coordination is there within your material. So in this example it is shown that this blue one is chromium in +6, chromium oxide or chromium in +6, and red one is chromium in +3 oxidation state. So first one, this sharp peak is present only in case of blue, but the another chromium oxide, this one is not present. So this first peak represents pre-age peak, and this one is the absorption age, the sharp rise. So this pre-age peak is comes because of the transition from this core S orbital to D orbital. Now you know that this S to D is not allowed transition, because then how this pre-age peak is coming? It is possible only when this transition is allowed. Now in case of chromium +6, sample is tetrahedral symmetry. So in case of tetrahedral there is no center of symmetry, so that means in this case this DP mixing is allowed. So that's why this 1s2 3D, this transition is allowed, and because of that we get a sharp peak for this chromium +6, whereas in the case of chromium +3 it is absent. So from this nature one can tell about the coordination chemistry of the material. So this is a typical beamline setup. This is taken from, this is a P65 beamline where we went to perform the experiment last time. This is in basic photon science source. Yes. And sir, I have a video. Can I show? Okay. So now if you want to understand basics about like how synchrotron radiation or how this powerful X-ray is generated, and how they are utilized to measure sample, in that I am showing you from a YouTube video. Okay.